好，那我们评审老师，我们看要不要就都统一用这一面哦？那背面的话就是当草稿。
哎，我这里写1。
对，你是第5位评审。对，就是统一都用有抬头的这一面，是不是？对。那后面是给大家当草稿的，是不是？
对，然后评分完要记得在这边要签上
名字，就这一面为准。那这后面就是草稿了，那不用也没关系，有需要的话就可以背面当草稿，然后以前面这一页为准。然后这边要记得签名。
那有白纸。
那还有提供白纸。
可以稍微记一下学生的表现。有被子用。
现在是可以了吗？所以可以开始了，对不对？你们会时钟吗？好，好，那我们就开始喽。那就是开始那个 opponent challenge please for 1 minute.
P1 challenge your problem number 6. Magnetic mechanical oscillator.
We accept the challenge.
Okay. Thanks.
好，那就是这个负责 6 的同学，请把名字写上去。不是，你要换下一个了，现在已经到那个 prepare 5 minutes。prepare 5 minutes。好，开始。现在就是 prepare 5 minutes 吗？还是这样？对，要再跳到下一个，再跳到下一个。
We accept the challenge.
对，所以你按错了，
他按 reject。
对，好，确定。
叫他们连分贴不要连分贴。
你刚刚选6吗？接受了。好，所以现在是到了。这个早就过掉了，在干嘛？对 ，opponent charge 是6，好，到下一个。
We accept， 我们接受第6题。
对，到下一步骤啊，因为你要
下面写我们把1题 reject 了。
好 reset 好，对，所以可能我们工作人员也要熟悉一下。
它下面是 reject。
就 reset， 按 reset。
跟你程式有问题，程式写的程式有问题。就是写东西。
好。
之后再改用。那边可以。
是这样。
accept 对不对？好 confirm， 然后这个呢 ，opponent challenge 的这个没办法改。可是 opponent challenge 怎么可以 reject 呢？这边没有无所谓 reject 啊。
不是他的意思是说，我已经 reject 第6题，所以他叫我再选，他请 opponent 再选下一题。但是事实上我是accept 这第6题。
对，这样我们就没办法再选第6题做报告。
就一开始点错了，然后就没办法改。
对 ，yes。还是我们先随便按一个，
怎么样？你知道怎么用吗？还是？他们没有 reject， 他们超接受的，但是因为工作人员按错，那叫什么？想问一下，就是有人工作人员按错。所以你真的没办法回去，是不是？你是退不回去了，对不对？
就是这边改 accept 之后，它就是这边
还是你重新
还是你退回去，然后把那个关掉，再重新开始，重开一次。
他们会在纸本上记清楚，所以看起来程式是没办法。好，重新再开一次看看好。 的连线电磁化连上我暂时没有用。
可以按照Control对。
好，可以哦。好，我们再重新选一次看看，如果不行就没关系，我们就往下进行，在纸本上再处理清楚啊。因为刚刚问的好像是不能改。好 ，continue。好，小心哦，第6题。
不可以直接按。
好，那 accept 那确定。好，那你开始准备5分钟了。好，这样应该 OK 了哈。所以那个我跟你讲，一下子他们可能比如说不见得到5分钟，他们就要跳到下一步，你就可以跳到下一步。或者是说他们报告的时间虽然是这么长，可是他们可能就说那就好了，就跳到下一步。那最容易发生问题的是在那个，就是比如说一个是工人问完然后有一个讨论的那个时间，那个地方是最容易有变化的，因为他不一定要问问题问嘛，他可以说我现在要开始讨论。对，那个时候你要记得说，那就是他听到这样子的过程就要做切换，要把它切换到开始讨论。对对，我尽量记得但是不算相反。对啊，因为你可能明天碰到别人，不是每个女生都这么非常完美。对的。对，然后你现在看这个哪或者是说也不一样，哪个应该会写在我们上面。好，那下一步。Reporter, please.
Our team is Minzame and I'm King Chen. And our topic is magnetic mechanic oscillator. And here is the problem statement. And we highlight that we attach magnets to the RBNS and repel. And we are going to investigate the relevant parameters. And here's our main focus. We are going to focus on how to convert Lilly's simple harmonic motion and get a decay coefficient and situations. Find the magnetic and dipole moment. And experiment 1, relation between mass and period, and it is about 1 ruler. And experiment 2, relation between distance and period, and it's about 2 rulers. And experiment 3, relation between mass and period, and it's about 2 rulers. And here's the demonstration video. And as you can see, The passive one will be affected by magnetic force and then move to left. And after a few seconds, you will see coupled oscillation. And these are our equipment: force sensors, bricks, and magnets, Gauss meter, and aluminum ruler. And first, let's talk about one ruler. We have to prove whether it is a simple harmonic motion or not, and use stem equation to gain its motion. Here we consider the resistance and the elastic force. Our purpose is to find out the function x of t. So according to Newton's second law, we can write down this equation. After calculating, we can get a depth omega, and here we add damping into this function. And to add it to this function, we can get this. And let's go on to two rulers. Compared to the equation of one ruler, it additionally has magnetic force. So now we are going to get a relation between distance and its value of the force. Here we use the magnetic dipole moment to get the magnetic field, and then turn it into magnetization vector. After obtaining big M, we can get the equivalent current density. And here we integral magnetic field over the thickness of magnets. Eventually, we are going to use the term of electrostatic force. We have to get the density of magnetic charge times its surface area to get magnetic charge. So here we can get the value of force, and we put it into the equation right here. And before going to experiment 1, we have to confirm the equivalent spring constant of aluminum ruler. We choose 4 distances and put it with force sensor. According to the value of slope, we can get a constant 12.53. And here's our steps. Setting a camera and use slow motion. Put a ruler to a marked rotation. Start recording and then let it move. Use checker to check its motion. Our relevant parameters is different quantity of magnets. Because we have got the spring constants and mass of magnets, we can get a theories omega. And here blue one is our experiment data, and the orange one is the theory's data, is the theory. And according to the function we get, we want to see whether the damping will affect the system a lot. And our theories omega of the 3 magnets is 25.23 right here. And as you can see, when we have 3 magnets on a ruler, its period is 0.249. The value of the decay is 0.114. And here is the quantity of 4 magnets. And here we got the theories omega is 22.05. When we have 4, the period is 0.285. The value of decay is 0.068. Theories of omega here is 0.315. Okay? And theories omega here is 19.95. And when we have 5, the period is 0.315. The value of the decay is 0.05. And we have a table right here. We found that the period is proportional to the square root of mass. And value of gamma is too small. We can confirm that the resistance doesn't have an impact on this experiment. By having a period and mass, we can indirectly get the equivalent spring constants right here. And because they are almost the same, so we take the average and get a 12.565. And it's very close to the value that we've got previously. So therefore we can see it as a simple harmonic motion right here. And before going to 2 rulers, we have to gain the value of the big M. And we use Gauss meter to measure the value of magnetic field, and we put the value into field support. We can get the magnetic dipole moment, and then we can take it divided by the volume of the magnet. We can obtain the value of magnetization, and this is according to the paper. And here is the value of the big M by different quantity. And our experimental relevant parameter is distance between magnets. The big T right here, and the big T is about the resonance period, and small t is about single vibration period, and gamma here is the decay coefficient. And the A is the active one, and the P is the passive one. According to the theory we got before, we can put it into Python to compare to our experiment data. And we found that the period of the theory matches our data. And so as the 7 centimeters. And if the distance is 9 centimeters, it doesn't have a coupling oscillation. We predict that the extremum of the range is from 7 centimeters to 9 centimeters due to its energy dissipative, and the magnetic force doesn't apply at the center of the magnet. And here we come to our discussion. The change when distance is 5.5 centimeters is most identical to the theory. The shape of the wave starts to have a little bit different from theory. Theory's extremum may exist from 7 centimeters to 9 centimeters. And according to experiment 2, we can find that 5.5 centimeters is the better one. So we choose it to change the quantity of magnets. The data of 3 magnets, which we showed before. And go on to 4 magnets. We also use the Python to stimulate, and we find it similar to our data too. And go on to 5 magnets. We also use the stimulation, and here's the table I organized. All of them are similar to theoretical chain, and resonance period is not affected. Here. All of them are similar to the theoretical chain, and resonance period is not affected by mass, and a single vibration period is close to the experiment 1. And here's the conclusion. The vibration period is proportional to the square root of the mass, and the resistance almost not affects to the system, and positive correlation between distance and resonance period. Extremum of the distance may exist from 7 centimeters to 9 centimeters, and the mass is not associated with the resonance period. Decay coefficient of the passive one is twice as big as the active one, and we don't find the reason why it is twice as big as the active one, because it might have some other resistance that we didn't think of, and it might be a little bit mistake. And because of the decay coefficient doesn't have a large impact on our system, and it is almost similar to our theories. So I think the decay coefficient is not the most important one. And here is my presentation. Thank you.
Opponent question.
For the first question, I want to ask, is the ruler S2 for long-term in your experiment?
Can you say it again?
Is your ruler S2 for the long-term in your, does the ruler always have the vertical to in your experiment? Okay, next question. And do you change the ruler in your experiment for every experiment?
We use the same aluminum rulers.
Okay, thank you. And next question I want to ask. So if you're in your experiment, you use your hands to pull up the ropes.
Yes.
Always.
Yes.
Okay, thank you. And next question, I want to say, do you think the whole system is all related to the simple harmonic motion? Do you think the motion is all related to the simple harmonic motion?
Yes, because we have proved that.
Okay, thank you. And another, I want to ask, so you change the magnet, you change the amount of the magnet in your experiment, right?
Yeah.
And another question is, I want to ask, so you also change the direction in your experiment, right?
Which direction?
The pulse release direction. You release the pulse direction to the different direction.
No, we use the same direction.
You use the same direction.
Yes.
Okay, thank you. And another question is, have you measured the magnet field in your experiment? You measured?
Yes.
Yes. Okay. And another question I want to ask, do you think the air resistance is important in the experiment?
Probably not.
Probably not. Okay, thank you. And another question is, I want to ask, do you think the two poles have the regular movement?
What?
Do you think the two poles have the regular movement?
I think yes.
Okay, thank you. And another question is, I want to ask, can your formula to set up to use
Time is
the...
up.
Okay, thank you.
Preparation of the opponent. Opponent, please.
So hello
Sorry,
everyone.
here's one thing that I should. No, I'm not.
Hello everyone, I'm the opponent Yezishi in team Omega for number 6 magnetic mechanical oscillator. And here is our problem statement, and we will focus to the movement of the springs. And here is our main focus. For number 1, we will explain the force analysis and function of coupling. And number 2, we will investigate how does the distance between two magnets and the amount of magnets and the length of the ruler affect the experiment result. And here's our overview of the report. And overview of the report, we can see the phenomenon between the magnets. They will have the oscillation, and from their report, we can see the zero for simple harmonic motion and the terms of definition. And for the experiment, they use the magnets with the ruler to the two sides and use the hand to move one of them. And also, they have the ruler for single ruler and to change the magnet on it. And they make the different distance between the two plates. And also, they have made the different quantity of the magnets. And for their report, the conclusion is the resistance didn't affect the system, and the mass is not associated with resonant period. And the experiment of the distance may exist from 7 centimeters to 9 centimeters. And the decay coefficient of the passive one is twice as big as the active one. And here is the advantage of the report and the suggestions for the report. So we think he had the good analysis of, so we think he had much experience data and do the good experiment to the report. And here is our suggestions. So we think he doesn't mark the symbol clearly and don't watch the phone and just read the words on it. And maybe it can point it on the report. And I think he needs to put the picture of the setup to explain her phenomenon here. And maybe he needs to put the unit of the grade. And here is our point to be discussed. First, we will discuss for the same rule for the simple harmonic motion and the terms of the definition in his experience. And we will also discuss further experiments for use the different quantity and use the one ruler to check the motion for simple harmonic motion and have made the different distance between the two plates. And accuracy, we think we need to add the arrow bar here. And thank you for your attention. And here we want to
begin discussion.
Yes. So can you change the page to number 9? Okay, and I want to ask, do you know what is this? Is the coefficient or some symbol for this symbol?
It's just a coefficient here because I want to use the magnetization to calculate the equivalent current density. So it is not important right here. It's just a coefficient.
Okay, and can you change the next page? So can you explain the picture here for the formula and what the relationship of it?
Here the function here is the Gauss slot, and the B is the radius of the magnet, and we integral the magnetic field over the thickness of the magnet.
And so what do you want to calculate the length here? Is the U or N or
The big N right here.
we want to calculate the big N. Okay, thank you. And can you touch the next page? So can you explain what's the formula want to calculate?
The magnetic force on the surface.
And can it explain your data?
Yes, because here's the Z right here is our which is we change, and it is the data we change. So
And also I have a question is, so in your 10, can you change the page to the 10? 10, page 10, page 10. So in your experiment, you also put this in your experiment. Here's the reason here. And what is the reason here?
it just
Yes. Yes.
it just a graph to to demonstrate. And I think it's not important right here because we just want to calculate the density right here. So we can have the magnetic charge, and so that we use the magnetic charge to times the magnetic field, so we can get the magnetic force.
Okay, can you change to the next one? Or 30. And what is the F here? Is the magnetic force?
No, I use the force sensor to pull the ruler, and the force right here. The force right here will appear on the software called Pascal, so we can get the data right here.
Okay, can you change to the next 16 page? 15. So you change the amount for the magnet here, and because in the simple harmonic motion, the formula is for the roots to the P to the body to the end, right?
Yeah.
So when you change the magnets here, you also change the weight here.
Yeah.
And the nets will not fit to the formula. Because you change the end here.
And the K is a constant, so it's about the ruler, not about the magnets,
It's the
not
mass.
about the rest of the
Mass.
mass.
When you change the magnets, it will change the mass in the formula.
No.
So the frequency.
The K is the spring constant, and it is about the ruler. Now, it will not affected by the magnets, the mass of the magnets.
Okay, next page. So here are the coefficients in your experiment.
You say here
Yes.
is the decay coefficient.
But you say it is not. But you always change the two variable in your experiment. Yes. You change the mass.
Yeah. And what?
Oh, okay, next page. Next page, please. To the variable 2 is minus 2.
2.
Yes.
Right here.
Yes. So, why do you put the magnet here? If you put here,
The distance will change, so we just put on the outside. If I put on inside, and the distance will change also. And let me think about it. We just maybe convenient to do the experiment 3, so it is
but
it is
in
not
your,
important.
In your
It's not-
conclusion, you said it maybe have the range for 7 centimeters to the 9 centimeters.
Yeah.
And do you think so the range, what is the range there?
I guess the range. And you can see right here, the 7 centimeters, it does have a coupling oscillation, but when it comes to the 9 centimeters, and it won't. So I think if the experiment exists from 7 centimeters to 9 centimeters, and if your distance is more than the experiment, and
So
you
you're
won't
saying,
have a coupling
so
oscillation.
you're saying it's in this system it only have the simple harmonic motion and don't have anything.
The magnetic force and elastic force and resistance.
But
Resistance.
in the experiment, you can know it has the 2 frequency, right?
You can see.
Yes.
You say the big T and the small T.
For the different pool, it will have the 2 different frequency, and one is the root to the K to the body to the N, and another is the root to the K plus 2 K body to the N.
Can Can you just write on it?
So there will have the two frequency and one frequency is the omega s, and it is the k divided to the n, and another is the omega f wrote in the formula, and it is the big K will plus the two big K, and this K is for the magnet, and it will also divided to the n. So you will have the two frequency, then it will have the couple, because couple is composed to the normal root, right? It will have the two frequency to compose the normal root, because the normal root will have the two frequency. So if the couple is the normal root, right? You agree?
Yeah.
Yes. If the couple is the normal root, so it will also have the two frequency in your experiment, right?
And what do you think the two frequency is on my experiment data?
Two frequency.
Yeah.
So
What do you think that?
when you change the amount of the magnet, and it will need to have the two frequency, because the couple oscillation, because the couple oscillation, it doesn't the regular, it is the damping motion, right?
Yeah.
So it is damping motion, and it doesn't have the regular motion, because it will big and then small, and the big and the small. So the frequency will change, and it doesn't only have the one frequency. So I think you need to correct the.
So here's the big T and the small t, and what do you think about my big T and small t to your omega s and your omega f? What do you think about it? What is the omega s to our experiment data?
Omega s.
Yes.
So because when your experiment, right, when you experiment at the range, and you can
I just want you to say which one, the big T or the small t. Which is the omega s. Which one?
you can calculate in your experiment,
Yes, but the big T can
because you
just run into the omega, but do you think the big T right here, if it transform into the omega, and do you think it is omega s or the omega f?
you see here is the cycle for the experiment, or it is the frequency just you say.
It's the resonance period, and the period can be transformed into the omega. So what do you think is omega s or the omega f?
So it can change in your omega. So when your period have the, so you can see it's like the omega s, and the wave of it will like this, and it will get small and big and small, and if you have the omega f here, and the wave of it will like this, it will have this.
But our experiment data doesn't show that. It's just
Because
just a little bit.
Because you say
decay right
it
here.
is the, because you just say in your report, so you think it is it only happened to the simple harmonic motion, right? But if the simple harmonic
Time is up. Summarize.
Thank you. So we discussed about the definition of the formula, and the reporter didn't put the experiment data into this formula. And the reporter thinks the picture that he put is not important, and if the picture is not important, I suggest that maybe don't put it on the PowerPoint. It's the better choice. And reporter put the quantity of the magnetic outside, and because the reporter think when we put the magnet inside will change the distance of the two poles. And we think when we change the amount of the magnet, the mass will also change. And it must have two frequencies, but the reporter didn't think about this, and also I think it had the damping motion in this, and the simple harmonic motion didn't have the damping, so I think it doesn't fit your experiment. And thank you for your attention.
Question of reviewer.
Yes, I want to ask the opponent, do your device use the infrared rays to detect the magnetic field phenomenon?
Can you say again?
Do your device use the infrared rays to detect the magnetic field phenomena?
Yes.
Next.
Magnetic field in the device.
Yes.
Have the magnetic field in the instrument.
Infrared rays.
Infrared rays.
Yes.
Can you explain it more? Yes, I think you will.
Okay. So, do you think that angle and position of infrared rays affect the experiment?
Yes, I think it will, because if you change the device, it just like the pendulum motion, and I think it will have the change in the experiment here.
Okay, thank you. And if the reporters chart which have the equation,
One more time, please.
if the reporters chart which have the equation,
Yes.
yes, and it's yours, and how would you fix or add something or design something in your chart?
I will. Can you say it one more time?
Okay, so the chart, you get it?
The chart,
Yes,
the data.
yes, yes.
Okay. Yes, I think it's the same thing. I think the same thing, and it will have the picture like this.
You agree their chart too?
I agree. I agree to their damping coefficient chart, but I don't agree to their wave chart.
Okay, thank you.
Thank you.
So the format of the chart equation, one of the chart equation. So why don't you use the chart line equation? Yes. So you use this one equation.
Yes, just. Yeah. This 2 minutes.
Yes.
Yes.
So can you explain why you use this equation?
We take of the crest of the wave, and we just want to see the decay coefficient is very big to have a large impact on our experiment.
So to predict the phenomena like this.
Yeah, and here we take out the E minus gamma T here, and we find that the period is fitting out experimental
Time
data.
is
So
up.
there is-
Reservation of reviewer.
Okay.
Reviewer, please.
However, on reviewer working with a public analysis magnetic mechanical accelerator. the problem statement, and the reporter needs to investigate how the movement of the springs depends on relevant parameters. And the next discussion to confirm it is. Yes, next thing. We can get theory density of the magnetic track regarded as electronic, and this are the conclusion. And the first question that I asked the reporter, they said that their device used infrared rays to detect the magnetic, and they think the angle and the position of infrared will affect the experiment. They agree with the opinion, and they agree with the opponent the chart of the equation that use the impression, not the straight line impression. So we can see the conclusion of the evolution period is proportion to square root of the mass, and the positive correct relation between distance and resonant period. Thank you for listening.
Concluding remarks for reporter.
The author has actually fitted the theory in presentation, and we discussed about the parameters in the theory and clarified that those are not crucial and trivial. And damping is not really important, which can be observed in the experiment 1. Proceeding to the experiment, we talked about the two kinds of frequencies the opponent mentioned, but our experiments didn't show her opinion right, since no obvious two frequencies be seen. And we have clearly shown our data in our demonstration video as well. So we conducted the experiment on our own. And here is our presentation.
Question of the jury.
May I ask all of you, can you show the page 22?
The viewer and the reporter. Jury is catching. Answer should.
Can you answer the question?
Yeah.
Yes, in page 22. I wish you, three of you to explain what happens in page 22.
Yeah.
Yes, can you explain this? We use 30 seconds.
And we just changed the distance between two magnets. And here's one thing that I touched on, because the control variable is the quantity of the magnets on the upper rulers. And we just
And then, can you explain what happened here in this page?
So they change the distance between the two poles, and because they change the distance between the two poles, and they use the same amount of the magnets on the upper, and also have the same length, so it doesn't change to the two variables in here in his experiment.
Thank you. And the first one. Yes.
They change the distance between the magnets, and data and analyze the data to the chart. Thank you.
Yeah, question please.
Okay, only to the reviewer, could you replay your slide, your presentation? I would like to make sure nothing missed on your presentation.
拉吗？你们接的就可以啊，
它这里没有写，
那边就有线的，接上去就好了。
插的，它刚刚可以，没有写。
没有切啊，那个没有切换。
再插上去，
是的，要切换。
不是直接就可以了。
刚刚是拔过，
把过。你要不要直接接这个？
对啊。
我拿不过去。
那我这边，哦。
不用啊，应该是不用啊，怎么会这样子？刚不是可以？
应该可以切换吧？
可以切换。
可以切换的，刚刚
切换的人没有切换开啊。
有没有切换的人？那个直接接。
刚刚有。
现在没有人要。
哦，现在不行，刚刚他们这样，刚报告的时候可以啊，没关系，没关系。
然后跳出来。
Let's replay your presentation.
还直接讲给那个。
接的还是不行呢。
哦，可能按照延伸荧幕。
直接把这个电脑拿过去。
还是直接拿去给问问题的教授看。
这个会点吗？好，再来，再来，没有了嘛，对不对 ？OK， 好，谢谢。
谢谢。
I think that is up. Please, going please. First of all, the reporter.都差不多哈，我们就把它翻到来。好，我们先 report。最低就是分的。 erase your. Five, 6, 6, 5, 7. Go to opponent. Eight, 7, 7, 6, 7. All the reviewer. Four, 6, 5, 3, 5. Take a break for 5 minutes. Please return in 40. In 5:40。然后现在呢，同学们，请们赶快换位置，就是呢换到你下一场角色的位置。那位置坐好以后，拜托赶快检查切换啊什么的连接哦。
Return question number 8.
Accepted. Challenge 8. Accepted. Please write down your name. Preparation of the reporter begins. please.
Hello everyone, I'm children from Team Emitter. Today I'm going to talk about the problem number 8, Euler's pendulum. And from our problem statement, we'll take a thick plate of non-magnetic material and fix a neodymium magnet on top of it, just like this picture. And suspend the magnetic rod, which can be assembled from cylindrical neodymium magnets underneath it, just like this. And deflect the rod so that it touch the plate only with highest edge and release it. Study the motion of such a pendulum under various conditions. And our main focus is study the motion of this pendulum, which is combined rotational motion and damping motion, and investigate how different parameters affect angular position and the period of the magnetic rod. And this is our experiment video. This is the first is side view. We just release it from the highest edge. And the second is bottom view. We use this to get a bottom magnet track, just like this diagram. And then this is our infer motion. The first is Euler's disk. It means regular rotational motion. And the second is under damping. It means angular position keep reduced over time. And the under damping, first we need to know the theta. The theta is the rotating magnet's angle, like just like like this. And the L is the length of the magnetic rod, and X is the distance between the rotating magnets. And we got these three, we can get theta. And for this formula, we can get this part. And this part, if this part bigger than the 0, it will like this diagram. And this diagram is like just the under damping diagram. But however, when we do the experiment, we observe it's not the regular rotational motion, it's the irregular. So it's not the Euler's disk, it's the uneven magnetic field in horizontal direction. And it's the angular position keeps reduced over time, but it's not the under damping because we can get the specific direction. We just use the positive flat to get this diagram. So like this diagram is the damping, but it's not the under damping. Then is the magnetic field of the horizontal. And the first, we just release it from the high edge like this. And it will like this part. And then it will swing to this side. And generally it will like in this. But however, it tilts a little. It's because the horizontal magnetic field is different. The y-axis is bigger than the minus y-axis, just like this. It's bigger. This is bigger than this. So it will tilt a little and then swing to this side and continue to swing. And then is the magnetic field. And when we get the magnetic field, we integrate it and we get the magnetic moment per unit volume. And it will like this formula. And the magnetic moment per unit volume equals to the magnetic dipole moment divided by the volume. And the volume is the pipe, and B is here. And B squared and L. Then we can get this formula. And finally we can get a Q. Q is the magnetic charge. And when we got the magnetic charge, we can use this formula to get the magnetic force. And then is the torque analysis. First, rotation will like this. And R2 is the distance between the mass center and the contact point. And then this is the mass. And this is the magnetic force. And the magnetic 2 will the formula will like this. The sigma tau equals to R2 cross mg. And then the second motion like this. The mass is here, and the distance, and it's the distance between the magnetic force, vertical, and the contact point is R1. And the sigma tau will equal to R1 cross Fm and plus the R2 cross mg is because it's in the same direction. And the third is the same as the number 2 motion. Then is the energy transfer. The sigma E equals to the kinetic energy and plus the rotational kinetic energy and plus the potential energy and plus the magnetical potential energy and plus the loss energy. And from loss energy, we do this experiment. And this experiment, the first we use the top magnet, and we just when it finish the rotate, it reduce the 0.7 degrees. But without the top magnet, it just reduced the 0.4 degree. So we infer it's because of the current effect, and it's the 0.3 degrees. Then we have the three parameters in the experiment, and the first is the amount of top magnet, and the manipulative variable is the amount of top magnet, and the control variable is the thickness of the plant, radius of the top magnet, length of the bottom magnet, and the end of the top magnet and of the bottom magnet. And then you can see the angular position. When the top magnet amount become bigger, the decrease trend will be slower. Just you need to see this part, this number, it decrease. And then it's the time consumed. Because the magnetical potential energy is about the same, so the sigma E about the same, the time consumed will about the same. And it's the period. Because the magnetic field about the same, the times about the same, so the period will about the same. And the second parameter is the amount of bottom magnet. And this manipulative variable is the amount of bottom magnet. And the control variable is about the same. And then is the angular position. When the amount of the bottom magnet become bigger, the decrease trend will be slower, like this. And then is the time consumed. Because the magnetic field is decreased and is the minus, so the sigma E will increase and the time consumed will increase. And the period, because the magnetic field is decreased and the force will decrease and the time will increase, so the period will increase. Then is the thickness of the plant, and the manipulative variable is the thickness of the plant, and control variable is also the same. And the angular position, you can see the thicker the thickness of the plant is, the slower the decrease trend will be. Then is the time consumed. Because the magnetic field will decrease, just like this picture. When the distance is bigger, the magnetic field will decrease. And because this is minus, so the sigma E will increase and the time consumed will increase. And this is a period because the magnetic field is decreased and the force will decrease and the times will increase. So the period will increase like this diagram. And that is our conclusion. The Euler's pendulum combines irregular rotational motion, pendulum, and damping motion. And when the amount of top magnet increase, time consumed and period are about the same. And when the amount of the bottom magnet increase, time consumed and period increase. And when the thickness of the plate increase, time consumed and period increase. And for three parameters, if the angular decrease trend will be slower. All of them is slower. And thank you for your attention.
Questions of opponent.
Okay, so do you think like the heavier the pendulums, like, do you think like if you add like weight or something, will the pendulum like swing faster?
Okay, I'll say that again.
Do you think like if you like add like weight down there, like
Weight down there,
like if you add weight,
add weight.
like add weight,
Yes, okay.
do you think like it will swing faster?
So spin faster.
Like, do you think it like matters?
It's not the main cause. It's because of the magnetic force.
Okay. And like, do you think like the friction slows down like the pendulum? Like the pendulum? Do you think like the friction matters? Like the pendulum to like slow down?
Friction.
Yeah.
Yes.
Like, okay. And like how? Like,
Friction like the air resistance, it will affect this experiment, but not the main cause.
wait, can you say it again?
Like air resistance is the friction,
Right.
but not the main cause.
Okay. And like, do you think like when like the pendulum like stops, do you think it's because of like the gravity or something? Do you think it's because of the gravity that stops the pendulum?
Gravity.
Like gravity.
Gravity. Can you explain the gravity?
Like gravity means like when like just imagine like when an apple like drops down, like that's all gravity.
Oh yes.
Yeah, so that's that.
Yes.
Like, okay. And also like do you think like the way they swing also depends on like the
Time is up. Preparation of opponent. Opponent, please.
okay, so like for their main focus, like they study the motion of this pendulum, which is combined random frictional motion and damping motion. And for the parameters, like
the three amount of top magnet and amount of bottom magnet and thickness of the plate. And their analysis is the first analyze time consumed and the period. And for the conclusion, it combines the irregular rotational motion, pendulum damping motion, and when the thickness of the plate increase, the theory. And like their pros is like they actually explain their formula very well, and they also kind of explain the formula with the chart. I think I'm just gonna start the questions. So can you just kind of show the data at page 12? Can you just describe why is the error bar this way? There? Yeah.
It's because the amount of time is just 5, and the magnetic force is too small, so it will like this.
Wait, but why is between 20 and 25 is also 50? Yeah. There.
There?
No, the first one. Yeah.
And
why is it all like this? Because I cannot actually relate what you're explaining to that.
You mean it's an error bar? Because the magnetic has an uneven magnetic field, so it will affect the error bar.
Okay. Then can you just turn to the formula?
Nice.
Can you try explain it again so I can really understand it? With that picture.
Like this picture.
Yeah.
Okay. And this is the magnetic field, right? And we just integrate it, and we can get this formula. And this formula we can get a M. M is the magnetic moment per unit volume. Okay, understand? Okay. And it's equals to the magnetic dipole moment divided by V. And the V is the volume. So when this volume is need to use the V is the radius of the magnet radius. And then you just use the pi and pi b square and use the L. It's its volume. Yes. So you get this, and then you can get a Q. Q is the magnetic charge, and finally we can get a magnetic force just like this. Okay. Finally we need to get the magnetic force. So we get the magnetic charge first and get the magnetic force.
Okay, then can you turn to page 11? I'm just wondering why is data up and down? What is
Up and down?
Yeah.
Okay.
Can you just guess why?
Because it's up and down just like this.
Yeah.
It's because it's swing. So its angular will be small and then be bigger and small and bigger.
Yeah. And what's other variations that you think will matters to the frequency?
Frequency.
Yeah.
The other.
Variations. What's other variations that you think will matter?
The magnetic field and the length of it and the magnetic force.
Yeah. I mean besides Zen and force and all that.
What?
Can you think variations other than Zen and force?
Or other than that?
Yeah.
Maybe the contact area. The contact area will affect this.
How? How does it matter?
I don't do an experiment. I just can infer this to you. So I think contact area. And maybe we can draw this. Because this is the plan of it, right? And we have the half magnet. And then it's the magnetic rod, and this part will inflate. It will over this part. The contact point of this part will affect it. The contact point, yes. The contact area will affect this because the contact area be bigger, maybe the friction will be bigger, damping will be more. The damping will be bigger.
Oh, yeah.
And like,
Can you also turn to like the page 13? Like page 13. Okay. Like, I think like page like wait. Yeah, page 16. Yeah. And like I'm just wondering like why the air bar is like kinda like it's not like small, but like it kinda go bigger right there and like when small again and then go bigger.
it's also because the uneven magnetic field, so the error bar will, it's not a regular, it's just the error in this experiment. Yes, and yes, just like this.
Okay.
And why do you think like this pen like goes up like that? Just like this pen goes up. Why the pen goes up? Well, because the magnetic field will decrease because the length be bigger, the length be bigger, the magnetic length be bigger, and the magnetic field will decrease. And then because this is decreased, and the formula this is minus and decrease. So the U magnetic will be increased. So the U magnetic increase, the sigma energy will increase, and then the time constant will increase.
And can you also just show this like kind of like draw out something like for your experiment device?
Draw.
Like or just like explain like how to like what's your like experiment device?
Draw my setup.
Yeah.
Okay. Actually we use the desk. The desk of it, and then we put the top magnet on it. And then this is the magnetic rod, and it's assembled from the cylindrical magnets. Just like this. So we just release it from the high edge, and it will swing like this.
Do you like keep like the angle that you like put over here like the same?
Yes, because we just release it from the highest edge.
Oh, you just choose it for like height.
Yes.
Isn't it like you choose it for the highest one for like every like experiment?
Yes. Every experiment because of the problem statement, you want to see that?
Yeah.
Because of this. Let's say you need to touch the plant only with highest edge. So in the experiment video, we just put it the highest edge like this, and it will swing and like this.
Wait. And like, can you just like describe it like how's your formula like related to your experiment?
Formula?
Yeah. Like how's it like related?
This picture or
Like this one.
okay, like this one. Okay, and for this one we need to get this part because I just turn it to you. We have three kinds of damping, and if this part bigger than the zero, it will call the under damping. Automatic, it will like this. So it will like this under damping. The diagram will like this.
And why do you think like the circle damping is like that?
No, you said this experiment. This experiment not the under damping. It's just the damping because it not have the specific direction. Do you want to see that page?
No, I can do that.
Okay. And if this part equal to zero, it will like this. The diagram will like this. So it's called a critical damping acceleration. And if this part is smaller than zero, it's the over damping like this.
Can you like page number 9? Okay. Like, I think page number 9, you said that you use like the top magnet first. Like, what kind
First we just like this, we just use this like this. We got a top magnet of it, and we just measure it the whole experiment until it finished. So the whole experiment will decrease the 0.7 degrees. And but next we just without the top magnet, just like this picture, this setup, the top magnet without without. And so the whole experiment just reduce the 0.4 degrees.
Oh, okay, so there's like for the experiment, you just want to see like what's the difference without a top magnet.
Yes, we just see that, and we infer it's because of the current effect.
Like how?
Because the top magnet have the magnetic force, right? And it will cause the current effect, and it's 0.3 degrees.
I think I'm totally it.
Summarize, please.
I asked the reporter that does she thinks like, will the heavier, what if they add weight, will the swim faster? And she said yes. And also I asked her the question about like, do you think it also depends on the degree of the amplitude? And she said yes too. And also, for like the top magnet, like eventually like the temperature like goes down a little bit, so they have like current from it. And she also thinks that the friction also slows down the pendulum.
Questions of the viewers.
Okay, so first question. You have mentioned about the longer the pendulum is, what will happen to the period? Can you repeat that again? The longer the pendulum is, what will happen to the period of the pendulum? Yes.
It will the angular position decrease trend will be slower, and then the time constant will be bigger. Will be higher, and the period will be higher too.
What do you think about the meaning of the slope? What do you think the meaning of the slope is?
Meaning of the slope,
Yeah, like increases over time.
this is increase because the magnetic field decrease and the force decrease and the times will increase, the period will increase.
And can you explain about the energy loss again?
Okay. First we do the experiment like this, and the first way with the top magnet, and the whole experiment will reduce the 0.7 degrees, and then we use this setup.
Okay.
And then this is without the top magnet. So the whole experiment just reduced the 0.4 degrees. So we just infer it's because of the current effect. And
May I ask you how you measure it? Like in which measure of time, like which seconds? How many seconds did you measure it?
how many seconds?
Yes.
How many seconds? I forget it, but I think it's about a second.
It's like extremely small, right? Seconds.
A second?
And maybe we can just move on to the next question. Do you think in this experiment, do you think the magnetic force impacts more than the energy loss?
Okay, so in this picture,
I mean, in this US pendulum, do you think the magnetic force impacts more? I mean, impacts strongly than the energy loss?
yes.
Yes. And what do you think? In this experiment, do you think the energy loss impacts minorly, relatively to the magnetic force?
Okay, yeah, definitely.
Okay. And also, okay, turn to a conclusion.
can you explain number 2 again? Why does the time consuming period are policy for the amount of top mechanical increase?
Okay, because the magnetic field will about the same, so the time console and period will about the same, and we do the experiment to explain that. Do you want to see that?
Okay, thank you.
Time is up. Preparation of viewer. Reviewer, please.
Good afternoon, everyone. I'm a reviewer from Indonesia. Today, I'm going to talk about the viewer's handling. For the reporting, their main focus is on the equal motion is related to the random rotation and damping, and also investigate the parameters and how it impact the viewer position. An overview for the reporter, their advantage include they got a fair explanation of the phenomena, and they correct the phenomena is not conformed to viewer's test, and they take the energy transformation into account, which is quite good. And for the suggestion, their magnetic force is extremely good because they didn't explain the unit of it. And next one, in one of the schematic diagram, they didn't show the center of the magnet corresponding to the pendulum, and this might cause deviation. And next one, when measuring the temperature, they didn't mention about the time and the surrounding area, which might cause deviation as well. And lastly, for the demonstration video, they use hands instead of more precise apparatus, and this might cause errors as well. An overview of the opponent her advantage includes she sees into the meaning in each diagram and asks deeply about how each force affects the system. And the suggestion for her include she didn't inquire about different questions as well. And discussion 1, the opponent asks about the reason for the error bar being evidently different by the amount of the magnet. And the reporter mentioned it's because of the different magnetic field. And opponent asks about the theory, and the reporter gives the explanation of the magnetic field formula well. And next one, the opponent asks about the variation matters to the frequency. The reporter asks respond to the length and force, and the contact area might also affect. And she also demonstrated the impacting by friction of the contact area. And discussion 3, the opponent asked about the setup, and the reporter explained it by drawing. And for the next question, the opponent asked about the energy loss, and the reporter mentioned that by temperature, it is still However, the reviewer thinks that it's still quite dubious since it's not clear enough. And finally, it's our conclusion. When measuring mixed temperature, it should have the clear condition and also show us the surrounding area, how it's like. Yeah, and also she didn't take different releasing conditions into account. Like she released it like statically, but she didn't take into account the acceleration if we release by different condition. And she also needs to find out another way of releasing, not just by simply by hand, since it might cause the three-dimensional force rather than the two-dimensional force. And she also didn't explain the energy loss well. Like what we mentioned, she pointed out she can't remember what the seconds of it, because like the temperature loss can be quite quick, and we are not sure how did she manage to do that. And this is much of my presentation. Thank you.
Closing remarks, please.
And thank you for opponent and reviewer's suggestion. I will continue to work on. For my report, it was pendulum combines irregular rotational motion, pendulum, and damping motion. Depending on magnet, we have successfully grasped how to get the value of magnetic force. And we also describe the energy transfer and find the form of the energy loss. And while the annular bar is sometimes bigger and sometimes smaller because of the uneven magnetic field. And the oscillating will not be the regular motion, and discuss about the damping, and this motion is not the anti-damping. The reviewer asks when we measure the energy loss, we measure it from the beginning to the 10 seconds after it starts to move. And also, we measure the energy loss, the second of the energy loss, and we also measure the contact area. And the energy loss. And yes, and thank you. And thank you for your attention.
Question of the jury? Any question?
I have a question for three of you. Let's address on this page. For you, you first. Do you understand why she said you didn't explain the energy loss well?
Yes, because I just said I forget the second of it, but actually we do it, and it's 1 to 10 seconds.
1 to 10 seconds?
Yes.
So very short time range.
Yes, because the magnetic force is too short, and so the second is short, very short.
Then how about find out another way of releasing? Yes. Do you know what's the suggestion here?
I don't know because I can know what about what's her meaning, because the power statement is we just release from the highest edge.
Okay. Then how about you? Addressing the 2 points that I just asked. Does she explain the energy loss well?
I understand a little bit.
Wait, can you say your question again?
Do you know why she did not explain the energy loss well? Why?
I think it's because of the time that she just said.
Okay, the time is short. And then how about the second one? Should find out another way of releasing. Can you understand what is the suggestion here?
Yeah. So because she like releasing, is it means like she release like her like sweeping from like the top? Do you mean that?
Yes. Why she suggests to release?
From the top?
Not from the top. Try to have another angle.
Oh, wait, do you mean like why she like do her experiment from the top?
Yes. Why not?
Yeah, because I think like I just asked her like she said it's because of like the problem statement.
Uh-huh.
Like because for like the problem statement they said that release your pendulum from the top.
If she did not do that, what happened? if she did not release from the top, what will happen?
It might not have like, and like, I guess, I don't know, like, I think if she actually released it from like different angles, it might have like different results for like, I mean, not only like, your like, friction, no, frequency.
Okay. Then the last one.
The thing about the energy loss,
Mhm.
yeah, she mentioned about the seconds, but as well, she didn't mention about the surrounding temperature. Like when the temperature is high, it might not decreasing as fast. And the second, I think the collision of the pendulum will also have the impact on the energy loss as well. And the reason why we mentioned about another way of releasing is because that the hand force is actually a three-dimensional force, and you can impact it by your simply hand shape. Hand shape will also impact. So we think it's not precise enough.
Oh, it seems that is not precise enough.
Yeah.
So you suggest them to change a little bit and try to find out the error bars.
I think maybe just use another more precise apparatus. Yeah, and also it will affect its initial condition as well. Like the different people, it will also have different results, we think.
I got it. Any short questions? If no, marking please. First of all, the reporter. Seven, 7, 7. For the opponent. 6, 4, 7. For the reviewer. 8, 7, 9. Thank you for all. Take a break. Please return challenge, please.
We want to challenge question number 3, Siren.
Please write down your names. And the lovely preparation for 5 minutes.
Yes.
Reviewer, please write down name.
change this to result for OBE are here and you overcome.
Report, please.
Hello everyone, I'm Carol in Group and I'm going to talk about question number 3, siren. Topic: if you direct an airflow onto a rotating disc with hose, a sound may be heard. Explain this phenomenon and investigate how sound characteristics depend on the relevant. And this is our experimental device. And this picture is our experimental purpose. We want to know the relationship between hole speed and sound. We measure the sound and observe its frequency. And this is our experimental device. And we draw a hole on the wood and we put a model in here. And we stick CD on coil here and fixed coil on the model. And we will change our CDs and ampere. Ampere we will change back here. And this is our principle. We found this principle in official videos, and it's a reflection follows as airstream pixel area each host. Compression waveform as airstream passes through host. Basically, we brew the string like this picture, and air particles will be pushed in here. And air particles will be stuck like holes between the holes. And then CD will keep rotating, and the air particles will through the holes. And air particle will like this picture. There are in-sport and low-sport, and then it will become a longitudinal wave to make some sound, and we can hear that. And this is our variation. We draw 3 circles on the CD like 1 and 2 and 3, and their radius like 1.5, 3, and 4.5 centimeters. And then we draw holes on circle. Like here is holes, and this holes radius is 0.02 centimeters. And then we will change the holes, the number of holes on the circles. Like this one is we draw 12 holes on this inner circle, and 24 holes on middle circle, and 36 holes on outer circles. And this is another variation. We change CD's rotating speed. And these models, we use these models. And these models RPM is 13,000 and 2000 to 14,000, 1900. And we change the ampere to change the rotating speed. And we can know when higher the ampere, the higher the speed. And this is our experimental follow chart first we blow the air with a straw with our experimental device, and we will get audio files. And then we put these files into sonic tools, get audio frequency, and then we will get every frequency, and we will get 3, and we average it, and we put it into Excel to make charts and upload the phenomena. These 5 charts are 5 different kinds of CDs, 3 circles frequency. Let's take the most obvious picture. And this line is ampere. It is mean the speed, and this is slower, and this is faster. And we can see this is frequency. And we can know that the higher the speed, the higher the frequency. And then we can know this is outer circle and this is inner circle. And big circle will, the frequency is higher than inner circle. And it is because that the more holes will be passed every second, because outer circle has more holes than inner circle. So the faster one and bigger one will have higher frequency than small one and lower one. And this chart shows that these charts are CD's outer circles audio frequency compression. We can use this chart to check out that if number of holes passes every second will affect the frequency. Look at this deep blue one and light blue one. We can know deep blue one has 36 holes on the circle, and light blue one just has 9 holes on the circle. So deep blue one has the higher frequency than light blue one. And these 2 charts showing that we draw the same number of holes on different size circle. We can find that no matter what big or small circle, the size doesn't affect the frequency. It is because the same number of holes passes every second. Make a summary. We can know that the main thing affect the audio frequency is the number of holes. Therefore, the faster speed is also mean there are more holes are passed. That's why in some frequency can be. That's why in some frequency can be detected. We guess it is because the frequency is too slow, and the snow need towards isn't scientists enough.
Opponent, please.
Hello, I would like to ask, do you think that the disk vibration might create a frequency? Do you think that the disk vibration might create a frequency?
Yes.
Yes. And my next question would be, when the disk does not spin and you blow it, does that create a frequency?
No.
Cool. But, that will be like one of my important things that I'm going to discuss later. And please turn to page 10. When the ampere is 0, do you think that there will still be a frequency?
But I think we won't have frequency.
There will be a frequency?
No.
There will not be a frequency. Okay. And then, in your way of analysis, does it mean that you can only test one kind of frequency?
Yes.
Yes. Okay. And in your prospection, do you think that there will only be one frequency?
No.
No. Okay. And when the airflow angle changes, will the frequency change?
I see it won't.
It won't.
we track it.
Okay. And in your experiment setup, did you use a straw to blow it?
Yes.
Oh, yeah.
Time's
That's all
up.
my questions.
Opponent, please.
Okay, their problem statement was siren. If you direct a airflow onto a rotating disc with holes, a sound may be heard. Explain this phenomenon and investigate how the sound characteristics depend on relevant parameters. Now, the summary of the reporter. The theory, they didn't have quite a reference for the theory. And the compression waveforms as it changes, but they talked about the compression waves forms changes their frequency. And then they also wanted to explain the relation between air particles, like dense or loose. Okay, and then their setup was a motor and a straw, which we believe that is not quite accurate. And also CDs with different circle lengths, and they changed the ampere, and also they had a analysis software. And the parameters they didn't change. Oh yeah, they changed the radius, like circle radius, and then different hole numbers, and also the speed. Like the higher the ampere, the higher the frequency. And their analysis was the outer circle and inner circle frequency differences between the density of the holes, and the number of holes will affect the most in their experimentation. And their conclusion was that when the numbers of holes affects the most, and also the speed also the spinning speed also affects the frequency, and as both goes up, then the frequency also goes up. And her advantage was that they had a clear apparatus picture, and they had a clear graph of showing the air particles. But our suggestions was that they should use, they thought that there wouldn't be only one frequency, so that we think that maybe you should use Fourier transform to observe the sounds of different frequency. And also they should try to quantify the rotating speed, which they didn't. And they should also show their main focus. And they didn't have an intercept in every single line, but they should explain what the intercept of the line would mean. And they did not show the references of their theory. They did not cite the references. So these will be the points of my discussions. Like short questions are the ones that I asked before. And then the long questions, which I'm about to discuss, would be the relation between frequency and rotating speed, and the natural frequency and driving frequency, and also the correction of their error, and another cool thing called overturn. And that would be the that would be the end of my presentation. Thank you very much. Can you first tell me, explain your phenomenon? Like, you thought that the sound, the sound is because of the airflow, right? Like dense and not dense. This is how it creates a sound, right? Okay. Another thing was that you found that the frequency is positively correlated with the quantity of holes, and also positively correlated with the spinning speed. Which do you think that you might be able to write a formula at? Do you think that you might be able to write a formula?
No, because I don't have the more clear frequency that you say. I just measure the higher one, and I don't have another low frequency, so I can give you the more clear. And our rotating speed is not very.
Okay, I get you. So, but what I'm trying to say is, I think that I might be able to write a formula for you. Since the number, your frequency, this frequency, is caused by how many times the air blows through one hole in every single second, which I can write into a formula is frequency equals not equal, but might be the quantity of holes, and times spinning speed per second. Per second. So in 1 second, how many holes I drew and how many times it spins will result in how many times one airflow goes through one hole. That would be correct. And let's see if this is true. Please turn to page 11. So when you have 36 holes and 24 holes and 12 holes, then you can see that it is about 3 times, which means when I have this is times 3, then the frequency is also times 3. Look at that 600, like 0.8 for it. When you have 12 holes, it's like about 200 and a little bit more, and when it's 36 holes, it's about 600. So this hypothesis might be correct. But when you look at with like 0.55, then the three times relationship that is not that clear. And why is that? In my first questions, you thought that it would not be there would not be a sound when you don't spin the CD. But I'm telling you right now is that there will be a sound. Like if you show the intercept of the line, as my second question asked, my second question, you would know that there will be an intercept and it would not be 0. So when you blow the CD, when the CD does not spin, there will be a frequency. So I might think that this plus something will equals to that. So now, as you see this, this part is almost always equal to that part. So when I have this, and these are all the same, right? So when I minus that, I will get this, which proves that my hypothesis might be correct. Do you agree that?
Yeah.
Okay, cool. So I wrote a formula for you. So my second question was that when you said you had only one kind of frequency, you can only test one frequency, but you thought that there will be many different frequencies. So we thought we gave you suggestions that you can use the Fourier transform, which you did not use, but yes. And why do I think that there might be a lot of frequencies when there is a disk moving? Do you think that it moves like this, or is it like this?
I think I wrote it. It's not hard enough to.
So it's like this, right?
No. It's sitting in won't move.
Like
yes,
this.
Another frequency will like be. I brought it the sound. I brought sound, not CD's move.
Not CD's move.
Yeah, because CD is stick on the wall. So
but there are different forces you apply to the disk. So the disk must be able to vibrate. And as I asked you in the first question, will the CD vibration create a sound? And you said yes. Now, so this is all preposterous. Okay, so you agree that this might happen, right? Give another example, like a drum. Okay, a drum. When I hit this, do you think that the whole thing will move, or do you think that it will move like this? This, right?
yeah.
Yes, that's what I meant. So if this is a CD, this thing was a CD, do you think it will move like this or this? So, so since it is not actually moving always in one kind of frequency, then it would change. There will be many different things, and that thing would be called overtone. Yes, that would create overtone, because one sound wave doesn't actually look like this. It actually looks like, depends on what kind of things you're using, like different instruments, different objects. They might have different like this or like that. That might be one sound wave. So this will cause something called overtone, which is also one of the characteristics of the sound that you can hear. Do you think so?
Yeah.
So when I have one major frequency, this is like, I don't know, 600, then there will be another frequency over here. It's because it's not like this, it's like that. So there are little up and down over here. So there will be other characteristics, which you did not do anything about because you have only one natural frequency. Am I correct?
Yes.
Okay. So, and now there will be some errors. It's like we thought that there will be a lot of errors in for experiments, right? Now I'm going to think that some of the possibilities of that would be to use you glue the straw.
Yes.
But you cannot control your breath that well that it creates a very, very steady flow. Do you think so? When you blow the straw, do you think that you can create a very, very good, like steady flow, airflow?
Yeah, I can.
You can't, which might be the possibilities of your errors. And in 1 ampere, do you think that the rotating speed will be always the same? But you don't have anything to qualify and quantify it, which might be something that you want to improve. Okay. And another question that I asked was when you blow the this is a disk. Okay, this is a disk, and you blow the disk in different angles. Will it affect? Yes. It will affect you?
No,
it
but
won't affect.
it's because I say that I'm very, very cozy, so the distance will not be very.
Yeah, cool. But
Summarize, please.
Okay, summarize, please. First, I wrote, according to their graphs and their statics, I wrote a frequency, a formula for them. This is like probably because of natural frequency. And then, second of all, we thought that there might be a other characteristics called overtone because they did not have the application or the device to do Fourier transform. So which might be something that they wanted to improve. And it actually fits the problem statement because the problem statement says observe the characteristics. And so this might be something under characteristics that you want to observe. And that would probably be it. Thank you very much.
Questions of the viewer.
The report that I want to read you.
Yes.
This page, like this part, didn't have the data.
I think it will the frequency is too low, so
So you didn't measure it.
yes,
Okay.
I cannot measure it.
Oh, you cannot measure it. Okay. And you say your airflow is not a steady airflow, right? Because you use the straw to make the airflow. So your airflow is unstable, right?
Yes.
Yes. And have you control the position of the airflow? Where you make the airflow, have you control? Okay, next question. Do you cancel noise in your experiment?
No.
No. Okay, next. Upon the, please imagine the disk without rotation but with the hole on it. Can you hear the sound or not?
Yes.
Yes. Okay. And so do you think the rotation of the disk is the main cause of this phenomenon?
You mean because that I can't hear the sound when the disk is not rotating?
Okay. And so so you say the rotation of the disk is the main cause or not the main cause?
Of what?
Of the disk.
Like When the disc is not spinning and I blow the disc, there still will be a sound that, yeah, but when it spins, there will be another sound, but the spinning will also affect, yeah, I agree, thank you.
Okay, and to successfully produce the sound, do you think there will be a limit on the speed of flow or the number of the holes?
Pardon me?
To successfully produce the sound, do you think it has the limits of the speed of the flow and the number of the holes?
Yes, I believe there will be a limit.
Okay, and do you think okay, and is the turbulence an important factor in this experiment? The turbulence is the unstable airflow.
What do you want to ask?
Is that the important factor in this experiment?
Oh, will not be a important factor, but might be an error. Might be an error.
Okay. And the reporter said she didn't cancel the noise, so you think it will influence or not?
Time
A little
is
bit.
up. Preparation, please. Reviewer, please.
Okay, hello everyone, my name is Insalchi. Today I will review the problem number 3 cyber. And here's the problem statement, and we think the main focus is the sound corrected. Okay, and we may focus on how host quantities affect frequency, and if the size of the host affects frequency, and if the rotational speed affects the frequency. Okay, and overview of the reporter. They observed the rotating disc can make a sound when the airflow through the hole. And the theory is rarefaction and density of particles. In the experiment, they changed the numbers of the holes on the disc and changed the ampere. In the proof, the investigation sticks to the problem statement and has many data on the experiment. And the count is no observation shown, and the video don't have the sound, and too much data on the same page. And the data no units and not see the trend line, and don't compare experiments and not manage the time. And summary, they overview of the formula. Summary, they discuss the formula of the frequency and also discuss the radius of the CD and the
direction of the CDs, and the process they ask nice question to the reporter and do some action to let the reporter understand. And the counts don't explain this test formula detail. And we discussed about the opponent asks, does this vibration only create one frequency? And the reporter said yes. And our own opinion is yes, it only creates only one frequency. But it may be because of the noise and create the overtone. And next, we discussed about the rotational of the disc is the main cause of this phenomenon or not. And the opponent say yes, and the reporters say yes because she changed the rotational speed. And our own opinion is yes because we can see it in the formula. And the missing point, they don't discuss the experiment that they change the amount of the holes because it will may affect the tone, and don't find the reporter data has no unit because the unit will may affect the breath, and the reporter is use the straw to make the airflow, and the airflow is unstable. And we asked the reporter have she control the position of the airflow, and she didn't respond me. And the reporter didn't cancel the noise in the experiment, so the experiment is not accuracy. Okay, and they didn't discuss the rotation speed in detail. So I think we need to discuss more. Okay, thank you for your attention.
Conclusion remark, please.
Opponent tell me the formula like that, and we need to put our number of holes and how fast with our rotating speed, and have some we don't know what is that noise and frequency, and have some another hole and rotating speed and we will get the frequency like that. And about echo structures, because I am very close the CDs and we brought is very close, so that I think it's very small, so it's too small for us to measure. And we just measure the higher frequency. Yeah, maybe like opponent says it will affect our frequency, but I think I'm brought a very not hard enough to move my CD, so I think it won't be affect my data. And reviewer say that I didn't take off my noise, but the audio files put out that is very small to hear that, so I think it's affect very small to my frequency. Thank you.
Questions for jury? Any questions? Please.
Very difficult to answer questions. You see in different levels. So, well, let me ask you in this way. Can you catch the idea that he told you, the formula over there, after he explains to you? Okay, and then can you take 30 seconds to explain that again?
You mean I need to, this one frequency is
How well do you understand this?
Yes, he want me to frequency, and that I check that right here and put my draw number of holes on CDs and here, and we need to know the rotating speed right here, and we need to add some, we don't know what is that frequency, and we will get this. And he said when this one I plug this one another frequency as rotating speed, we will get this one.
Okay, very well. And how about you? Can you explain that formula? What you just told?
So the frequency is equal to the numbers of the holes times the rotating speed. And it's set like that.
Oh, okay, very good. And then can you say that again?
The frequency is like how many times the dense and not dense part, and then so it will equal to the numbers of holes times how many times I spin in every second. Yes, plus the natural frequency, but yeah, but it will change into driving frequency.
Okay, can you explain what is natural frequency?
It's when, as I said, when the disc does not move, and then I hit it or I blow it, then there will be a sound. There will be a frequency, and that is natural frequency.
How about the driven frequency?
Driven frequency is when when you hit it too fast and it's bigger, the frequency is higher than the natural frequency, then the frequency will start to add up, and then will create a higher pitch.
Other questions? Please.
Do you really think the vibration of the disc does has some effect?
I believe so.
Why?
Because according to that formula again, then the vibration of the disc, there will be, when the air passes through the hole, then the disc will get, the force the disc receives will be smaller, and when it doesn't pass through the hole, then the force that the disc receives will be higher. It's higher, so it will create like higher force, lower force, so it will vibrate. Since it vibrates in that kind of frequency, since it can still be applied at the same thing, so since it vibrates the same frequency as that, then I believe it will affect the thing.
How about the effect compared to the rotating speed?
I think it would be smaller, not as big as
Small.
yeah. Huh?
How small? Or comparable?
I did not do this experiment, so I'm not sure that I can tell you that. But in my opinion and my logic, I think that it will not be as relevant. Thank you.
Not be relevant.
Will be relevant. I mean, not as relevant. Like it wouldn't affect as much.
Okay. So how about you?
You say the vibration of the CD. Okay.
Compared to the
compared to the
rotational speed.
And the airflow will through the hole on the CD, and when the airflow is the area is smaller than is bigger than the CD's hole, it will the force it will decrease. So it will let the experiment is not very accuracy, and the rotating speed it will it's a main cause of this problem. So I think the rotating speed is more important to the vibration of the CD.
How about the reporter? Do you think the vibrational speed, the vibration of the disc does has certain effect on that, or compared to the effect caused by the rotation, which one is bigger?
I would say in rotating speed is bigger because it is keeps rotating and is very fast.
And do you did you observe the vibration of this disc during your experiment? Really?
No.
Time is up. Marking please. First of all, reporter. Five, 6, 5, 5. For opponent. Eight, 5, 9. For reviewer. 8, 7, 6, 7. Thank you all for this